Formulation of porcelain enamels. Porcelain enamel has been a valuable material for kitchenware since the end of the 19th century, thanks to its rust-free surface coating, high level of cleanliness, and easiness to clean. This was when the technological breakthrough was made that allowed the elements of glass and iron to be firmly bound together. Porcelain enamel is the name given to a glass coating applied to a metal substrate, usually steel. The interface between the glass coating and the metal substrate is critical to the development of bonding between these two dissimilar materials. The glass coating must not only act as a protective and aesthetically pleasing surface, but also must bond to the metal substrate. Adherence. Before proceeding to a discussion of materials for porcelain enameling, a few words about the phenomenon of adherence are in order. For proper adherence, it is necessary to develop a continuous electronic structure or chemical bond across the interfacial area. As we'll discuss later, this is accomplished by saturating both the enamel coating and the substrate metal with an oxide of the metal. For iron and steel substrate, this oxide is FeO. Surface roughness also improves adherence, although it is of little value if the chemical bond is weak.
Ground coat enamels. As the name implies, the ground coat is applied directly to the metal substrate, often as an undercoat over which other coatings are applied. In other applications, the ground coat is used alone, especially when used as an undercoat. The most essential property of a ground coat is adherence to the metal substrate. Certain metallic oxides are added to the enamel formulation to promote this bonding process. Ground coats used as undercoats have comparatively simple alkali borosilicate formulations. Chemical resistance requirements are limited to minimizing surface defects that may be caused by the substrate or its preparation method. In addition, ground coats must have good workability under production conditions, which means low viscosity and low surface tension at firing temperatures. Table 4.1 gives some typical examples of general-purpose ground coat enamel. Coating A1 fires for 4 minutes at 805 degrees Celsius, whereas coating A2 fires for 2.5 minutes at 780 degrees Celsius. Occasionally, a fourth member frit may be used to produce an appliance gray speckled effect. Ground coat frits can also be designed to meet a variety of end-use purposes. For example, coating B4 in Table 4.1 has been formulated for alkali resistance through the addition of substantial quantities of zirconium oxide.
Enamels can also be formulated for thermal resistance in service. This is normally accomplished by raising the refractoriness or firing temperature of the enamel. Coatings C5 and C6 in Table 4.1 are examples of the formulations used when the outstanding thermal and corrosion resistance required of hot water tank systems are needed. A substantially different type of ground coat formulation is given in D7. This coating has been developed to provide a way to oxidize and hence remove food soils from the surfaces of ovens at normal operating temperatures. So now let's proceed to cover coat enamels. Porcelain enamel cover coats are designed to provide specific color and appearance characteristics combined with resistance to atmospheric and liquid corrosion, surface hardness, abrasion resistance, and resistance to heat and thermal shock, as required. Cover coat formulations are available to provide wide variety of appearance properties. They range from opaque whites through pastels and medium-strength colors to strong, dark colors. A wide selection of glosses is also available, ranging from the high-gloss sanitary ware finishes to the full matte architectural enamels.
Porcelain enamels cover coats are classified as opaque, semi-opaque, and clear opaque enamels. Are used for white and pastel cover coats. Semi-opaque enamels are used for most of the medium strength colors, and clear enamels are necessary to produce bright and strong colors.
Some fully opaque titania opacified porcelain enamels are given in Section A of Table 4.2. These materials have formulated to show excellent acid resistance and, in most cases, fairly good alkaline resistance. Titania opacified enamels are produced with reflectance ranging from 78 as with enamels A8 or A9 to 88% with enamels A10. Two examples of semi-opaque cover coats enamels are also given in Table 4.2. These materials do not differ in essential constituents from the fully opaque enamels. Instead, the concentration of titanium dioxide is reduced to the point where the system is compatible with the use of pigments for the production of medium-strength colors.
Clear cover coat porcelain enamels are used in conjunction with appropriate pigments for the production of strong and medium-strength colors. Some typical examples are given in Section A of Table 4.3. There is rather wide variation in formulation between these products compared with the opaque and semi-opaque enamels. Although same titanium dioxide is present in order to improve acid resistance, the concentrations are low enough that substantial crystallization does not occur. Therefore, the inclusion of pigment in the mill formulation will permit the development of strong colors. Particularly in the architectural industry, there is need of cover coat enamels with low gloss burst, with no reduction in weatherability and durability. Traditionally, this need was met by adding from 5 to 25% of silica or 2 to 10% titania to a high gloss enamel. There are several deficiencies in this technique. However, and recently coating have been developed scientifically for matte finish. In Table 4.3 includes of this coating. For example, B19 illustrates a fully opaque matte coating, whereas example B20 is a typical of a semi-opaque coating suitable for use with dark colors.
So that's all for our report. Thank you for listening.